Hi, thank you for coming to the first of my two talks. I'm going to be talking about non-positive curvature and biautomaticity and the space of currents. Maybe I should put a 1 here. So this is kind of an introductory talk, and there probably won't be that much stuff about currents in this. So I'm talking in this currents and representation variety workshop, and I'm definitely a geometric group theorist. I don't do this area of maths, but somehow something that I was working on with Motiejus, who's collaborated in all of this, required us to use the space of currents, and that was quite exciting because we had to learn about it. I'm going to kind of motivate the problem, explain like why you might care about this. This is kind of the background you need to like understand why the problem is interesting, I guess. And then in the second talk, I'll talk about some more detailed aspects of the proof, and kind of how it all fits together. So this is kind of going to be more group theory flavored. I'm not going to go into any like technical definitions. If you're more interested in the technical side on the group theoretic part of this, Motiejus is actually talking about this too. So he's going to kind of go into some more technical aspects of the kind of the biautomaticity. So it's kind of the first part of the talk. And how some of the kind of maths works there. I'm black boxing all of it, but I will give you some motivation about why these things are interesting. So kind of roughly, we have a finitely generated group G. So G finitely generated. By a set A. And then L is a set of words over A. And basically this is kind of the black box, is that it's going to be accepted by a finite state automata. So what this is saying is that L is a regular language. And there's some extra conditions, and basically this kind of gives you a biautomatic structure in your group. Now, I don't really want to say what that is, because this is kind of an introductory thing, but I will tell you some consequences of it. So basically the point is this gives you really strong algorithmic and kind of structural properties of your group. So for instance, we say a G has a biautomatic structure a curly L. And this implies a bunch of stuff. So this actually implies that you have solvable word problem. So kind of the classic algorithmic question. It also implies you have solvable conjugacy problem, which is good because that's considerably harder to prove in general. It tells you that your virtually solvable subgroups, so virtually soluble subgroups, are actually virtually abelian, which is quite strong. Puts some fairly strong condition on possible kind of subgroups that can show up in your group, so that's nice. This should be finitely generated. And also it tells you that finitely generated abelian subgroups, so in particular solvable, I guess, are quasi-symmetrically embedded. And this is sometimes known as the flat torus theorem. So roughly biautomaticity is this algorithmic kind of thing, which you have this language, which is just some set of words which represent group elements, and you can feed them into a finite state automata and it can tell you things. And this is very algorithmic. It's like you can implement this super efficiently on a computer. So like this gives you a very clear way to kind of build algorithms for studying your groups, which is something we quite like. However, where you pull out a biautomatic structure from is kind of usually a hard problem or often open. So you might hope that you can relate it to something else that we like in kind of group theory, which is curvature. So just kind of the general flavor of all of the maths I do is kind of in geometric group theory, we want a nice group action. Just put quotes around that on a nice space. Now, this is sufficiently vague, but we can make this quite precise. So the first nice is going to be kind of properly co-compactly by isometries. So I'll probably just say geometric action for the rest of the talk. And the second nice can be quantified as something that's a proper metric space. So this just means that if you take a closed ball, then it's compact. So this is just kind of a local finiteness type condition. And also you want that it to have some kind of non-positive curvature. And there's plenty of examples of these. So kind of the classic one is hyperbolic groups and spaces. So these are things like surface groups, fundamental groups of hyperbolic manifolds, free groups, free products of those things. There's kind of lots of these. They're quite abundant. Random groups, for instance. Then we have cat zero. So this is kind of, so whereas hyperbolic is kind of negative curvature, I guess cat zero is at most flat, so non-positive curvature. So cat zero is spaces in groups. This is kind of the class I think about the most, I guess. And this is loads of stuff with it. There's like Z to the N, free groups. It's open whether all hyperbolic groups are in this class. Has co-compact lattices. And semi-simple Lie groups. Coxeter groups. Conjecturally, so currently only some Artin groups, but conjecturally all. It's a big class. It's this big class of stuff, and we don't understand it very well. And in fact, like a lot of kind of counterexamples and weird constructions you can do in geometric group theory, you can actually make cat zero versions of them. So like even though it's this really nice class, like we don't understand a lot about it. And this is kind of a theme that will reoccur throughout this talk. There's another version, which is hierarchically hyperbolic. Spaces and groups. I'm not going to kind of motivate this one as well, but this includes things like mapping class groups. Yeah, like mapping class groups. Some cat zero groups are in there. A lot of cubical groups. So this is quite a big class. And again, this is more of a non-positive curvature, and it's like a coarse version of non-positive curvature. So a lot more things are hierarchically hyperbolic spaces than you might expect, but like being a hierarchically hyperbolic group is quite a strong property because there's this like complicated structure built out of kind of this hierarchy of hyperbolic spaces, and somehow you have to preserve the structure in a nice way, and then you're a hierarchically hyperbolic group. So not only do you act on this space, but you also act on this this structure which is built out of a bunch of different relations in the sense of set theoretic relations, and you have to really preserve this. So this is quite a strong property. And again, it gives you lots of all of these give you kind of conditions on your group. And there's also one more I'm going to mention and not motivate at all, which is injective metric spaces groups. And it's worth noting that there's an implication, at least on the level of spaces, due to, just on the level of spaces, due to Thomas Littell, Nima Hoda, and Harry Pettit, which has been out for a little while. It's a good paper. So this kind of is a really important thing, and just to make sure this is clear, this is only for spaces, this implication. Also, I should mention, just as another example of hierarchically hyperbolic spaces that's relevant to the talk, products of hyperbolic spaces. These are like the easiest example. There's one caveat. You can't have any quasi-lines, so nothing quasi-isometric to a line. There's numerous technical reasons for this. I don't want to get into them, but you'll see that it comes up more than once. So there's kind of like lots of different models for non-positive curvature you might take. There's super rigid ones like cat0. There's kind of really coarse things like hyperbolicity. There's this coarse non-positive curvature and hierarchical hyperbolicity, and then injective is very different, but somehow it's related to the others, and maybe this implication is some motivation for that. Okay, so there's kind of we've got a property which is good, and we've got a bunch of things we might want to show have the property, which gives us like algorithms and stuff like this. So in 1998, Nibler and Reeve showed that cat0 cubical groups are biautomatic. I'm just going to put biaut. So that's good. And then you think, okay, maybe all cat0 groups there, and then a full kind of 23 years later, I guess it was probably actually 20 years later when the preprint came out, but the published version is 23 years later. There exists gamma, quasi-isometric to a 12 regular tree, direct product with the Euclidean plane, which is cat0, but not biautomatic. See, okay, well that's good, because that's a cat0 group, and it's not biautomatic, so there we go, cat0 groups aren't biautomatic, and actually this thing is actually acting freely by isometries on this 12 regular tree and the Euclidean plane, so it's a subgroup of the automorphism group of that tree, T12 cross isom E2. So you think, okay, well that's like clearly I could maybe get like a hierarchically hyperbolic structure on this, because I've got this like plane that's made out of the direct product of two lines, and then I've got a tree, like the direct product of all of them, and you get a hierarchically hyperbolic space. But Jack Button proved that because of this extra equivariance condition, this actually came out a couple of days ago. Leary-Menashian's examples are not hierarchically hyperbolic groups. I'm not sure if they're injective or not. I'm fairly sure they're not. I couldn't find a concrete reference for this. But I'm not willing to say it's open. I suspect it's false. Okay, so this is maybe surprising. So in particular, we still don't know whether hierarchically hyperbolic groups can be biautomatic. So that's kind of an interesting question. And then also Margolis proved this result here, which is that if you have gamma acting geometrically on some product I equals 1 to n xi with each xi delta hyperbolic, or just hyperbolic, I guess, not qi, not a quasi-symmetric space. I'm just going to say quasi-symmetric. So what that means is not quasi-isometric to some Riemannian symmetric space, and not a quasi-line, so not Qi to a line, which is technically a symmetric space, but I'm just highlighting that this is included. Then gamma is biautomatic. So again, what's happened here is that we've taken we've got a product of hyperbolic spaces. I mean, basically anything which isn't like some hyperbolic plane or hyperbolic M space or whatever, some division algebra. And you just can take a product of these things, and any group acting geometrically on that space is going to be biautomatic. So this is loads of stuff. And like importantly, all of these are hierarchic hyperbolic groups. So this just proves that loads of HHGs are biautomatic. So you think, okay, great. So the counterexample is that you might hope that, well, the things that you might hope that would be a counterexample, these the Riemannian groups aren't. And then Margolis has gone and shown that like the simplest examples of HHGs, ignoring these symmetric spaces, are actually all biautomatic. So you think that's really good, but then disaster strikes, and this is kind of how the currents will slowly come into it. Me and Motiejus made a group. So there exists gamma quasi-symmetric to the hyperbolic plane and a 24 regulatory this time, which is cat 0, NHHG, it's injective, but not biautomatic. So we had to kind of work quite hard to prove this, and I will now outline some of the proof. So kind of the rest of this talk is just like motivation for how the proof works, and then there's kind of some technical aspects of it that are probably most interesting to people who study currents on surfaces, and I will kind of explain that in more detail in the next talk. But for now, it's just a very kind of gentle overview. I mean, there's still some work to do, but it should be understandable. Okay, so as in the previous case, we have that gamma, L group gamma, acts on HG across this 24 regular tree, and it's a 3D co-compactly. So we get a representation pi of gamma to PSL2R, thought of as isometries of a real hyperbolic plane. This isn't faithful, but that's not really important. It's just the group isn't linear. Okay, so now we need a definition. So first of all, actually, there exists a subgroup G of gamma, which is the fundamental group of a genus 2 surface, or isomorphic 2. Sorry. And G is a commensurated subgroup. So namely, this means for all G in gamma, G, the index of G intersecting each of its conjugates, and also the index of all of G's conjugates intersect G. These two indices, so I've said that already convolutedly, that's finite. So basically, if you conjugate it and intersect it, you can see a finite index of both of the two things, G and G conjugate. And this also has an extra property. So these are facts. I'm not going to prove these. I'm not going to explain where they come from. I think some of this might be in Motiejus' talk. But yeah, it's just important for us because the link to currents kind of comes out of this information. So we have this commensurated subgroup, and if we look at this representation, so we restrict it to G. So pi of G restricted to G just is isomorphic to G. So it's injective on this representation, and pi of G acts geometrically on H2. So actually you have a co-compact lattice and it's a surface group just acting on that. So we can look at the quotient and we get some Riemann surface. So it's this hyperbolic plane mod G. I'm identifying G with its image now, which is a complete abuse of notation, and I'm gonna do that probably for the rest of the talk. But hopefully it's clear. Okay, so we've got a Riemann surface, and we have this which comes from this representation of gamma, or at least like a subgroup of gamma. And there's kind of one more fact we need to tie everything together. So this is kind of a lemma, and maybe this is actually definitely in Motiejus' talks. G is L quasi-convex, which just doesn't really mean anything, but the point for us is this implies, oh, sorry, I've missed out something really important. So first of all, suppose there exists a biautomatic structure A L for gamma. Okay, so suppose for contradiction, gamma actually has a biautomatic structure. Then with respect to this structure, we have some notion of quasi-convexity, and the important part of that is that there exists an associated biautomatic structure, which we're just going to call B, M for G. And this is kind of defined in terms of the first one. So like once you've got a structure on gamma, you can find one on G. So now we just have a very clear goal, perhaps. And the goal that we have is to show that Bn is not compatible with this representation pi. So like we've got this surface group, and like this has lots of biautomatic structures on it, and basically we just want to show that this new biautomatic structure that we've got, gamma, isn't one of those. Like it doesn't exist, is the point. And then that would be a contradiction because, I mean, it couldn't have come from a biautomatic structure on gamma. So this is kind of the idea, or the goal, I guess. The idea is to extend functions defined in sigma over the space of currents. Which I'm going to denote my curly G plus sigma. Now, this is kind of maybe not obvious why you'd want to do this, but we have some kind of nice properties. So like pi on gamma actually is dense. So like somehow you might be able to use this, and there's a few other things that might work to kind of do this. But I'll just tell you what the functions are, and then in the second talk I'm going to tell you how we go about extending them, and I'll kind of sketch the rest of the proof in this talk as well, just to see how it all kind of fits together. So the first function is the translation length of G acting on H2. So equivalently, this is like lengths of geodesics on sigma. So we'll just denote this by TL from sigma. And then the second function, which is a bit more mysterious, is the stable word length with respect to n. So this is where the biautomatic structure fits in. So I will give you a definition of this. I'm not sure how insightful it will be, but first we set G with respect to m just to be equal to the min of the length of W as a word, such that W in L, sorry, W in M even, represents G. Okay, so this is kind of, you're just picking the minimum word length, and then we can define this stable translation length. So stable word length equal to the limit, then goes to infinity of a Gn with respect to this n divided by n. And then there's kind of an interesting fact, which is that at least Tm, so for now Tm is just a function sigma so you can identify G with a geodesic on sigma and then apply this function to it. This is just a function sigma to R, but Tm of sigma is actually contained in Q. And this is explained in Motiejus' talk where this comes from. For us, this is just a black box. So like this is kind of a non-trivial fact, but we prove that this function takes values in Q on geodesics. Okay, now the rest of this is a sketch. So roughly what happens by like a lot of analysis and kind of geometric group theory techniques and some, just math. Roughly what happens is we get the Tm extends, and also TL and Tm extend to functions from G plus of sigma to R, and we end up with Tm is equal to some constant times TL, where this constant is just a non-zero number. Okay, so it's worth noting that at this point we have one function evaluates on geodesics in Q, and the other function is translation length. So we could go and compute some translation lengths of G acting on the hyperbolic plane, and then show that they can't differ by like a rational number, and that would give us a contradiction because these two functions have to agree up to a scalar number, right? So that would be enough. So if we can find two elements of G which differ by a rational number, we're done. And actually, this is kind of good because the way to do this is we have a representation, so we can just go compute stuff. So I'm just going to fix a standard generating set for G. And I'm just going to pull these matrices out of the air. So the first one is this matrix here. Should have really prepared this ahead of time. It's occurred to me. So these are just kind of some matrices that come from this representation. I mean, I've listed them up to SR2, but I don't know, it doesn't matter. It's just a technical point that's not really important. So they look a bit gross. It's kind of unclear where these have come from, but I've built some quaternion algebra representation. That's kind of roughly where they come from. It's not that important. But the thing that's good is that we know how to compute translation length, because the translation length of G is just equal to 2 cosh inverse half the trace of G. Okay, this is like a nice advanced undergrad exercise. So what we get is that the translation length of A equals 2 log 3 over 2 plus root 5 over 2, and the translation length of C equals 2 log 5 over 2 plus root 21 over 2. Okay, so now if these differ by a rational number, then what happens is that we get 3 over 2 plus root 5 over 2 So the P equals 5/2 plus root 21/2 to the Q, and of course this can never happen, so it's a contradiction. Okay, so TL of A never equals Q over P TLC. Okay, so here PQ and Q not 0. But tau and sigma is contained in Q, right? And this is and we're allowed to multiply them all by a constant, but like you can never find a constant such that does not exist. K such that the translation length evaluated on sigma is a subset of KQ. Right, this is the point. So these two functions don't agree, but they did, right? That's like what we prove here. This thing here. So that's the contradiction we were looking for, and then this implies that gamma is not biautomatic. I will stop here for this talk, and I'll go over some more details about extending functions and so on. Thank you for listening.